Hello, good afternoon. This is the Unit 4, Periodic Table, Periodic Classification of Elements and Physical Properties, under BSc first year, Tribhuvan University, Institute of Science and Technology, Chemistry, first year BSc. First of all, periodic table, a table of elements arranged in order of atomic number with similar chemical properties appear in vertical columns. Modern periodic table consists of 7 periods and 18 groups. As block elements, the elements in which the last electrons enters in the s orbitals of the valence shell, that is the ns orbitals, are called s block element. Properties in general valence shell configuration, ns1 to 2, all are active metals. Generally, ionic compounds are formed from these metals. P block elements, the elements in which the last electrons enter in the p orbital of the valence shell, that is np orbital, are called p block element. Properties, the general electronic configuration, np1 to 6, ns2, p block elements are non-metals. P block elements forms covalent compounds. They have variable oxidation state. They form acidic oxide. They impart no characteristic color to the flame. Generally, they form ionic salts with active metals. D block elements, the elements in which the last electron enters in the n-1 penultimate shell of the valence shell, is called D block elements. Properties of D block elements, general electronic configuration n-1, D1 to 10, ns1 to 2. It consists metal only. These elements show variable valency. These elements generally forms colored compound. Most of D block elements and their compounds are catalysts. F block element, the element in which the last electron falls in the F subshells of the anti-penultimate shell, that is n-2 F orbital, are called F block element. Properties, general valence shell configuration, n-2 F1 to 10, 14, n-1 D1 to 10, ns1 to 2. All actinides are radioactive and other properties are similar to D block elements. Shielding or screen effect, the electrons present between the valence shell and nucleus are called intervening electrons. These electrons extend inter-electrons repulsion. The nuclear attraction on valence shell decreases due to repulsion. The decrease in nuclear attraction on the valence shell due to presence of intervening electrons is called shielding effect. Factor affecting the shielding effects, number of cells, greater is the number of cells, the higher will be the shielding effects. Example, sodium shows greater shielding effect than lithium. Nature of orbitals, according to wave mechanics, the penetration nearness of electrons in the orbitals to nucleus. Penetration means nearness of electrons in an orbital to nucleus. Power of electron in different orbitals of this given shell decreases in the order. Penetration power, ns, is greater, highest, and smallest one in the nf. Application of shielding or screening effect, it explains the variation of atomic radius, ns energy, from left to right along the period and top to bottom, deshielding down the group. Concept of shielding effect explain the cause of larger difference in ionization potential on moving from alkali metals to noble gases in same period. It also explained the cause of similar atomic size of element of second and third transition series belong to that same group. This concept also explains the lanthanide contraction. It also explains the irregular variation of atomic size in ionization potential element in group 3A. Diagonal relationship, the resemblance of properties of the elements of second period with the diagonally opposite. Okay, diagonal opposite members lying in the third period. See, lithium and magnesium, beryllium to aluminum, boron to silicon, carbon to phosphorus. Cause of diagonal relationship, on going from left to right along the period, the atomic size decreases, while on the moving from top to bottom on the descending group, the atomic size increases. However, on moving diagonally from one element to another element, these two effects cancel each other. That is, atomic size diagonal pair elements remains almost constant. This shows similar atomic and ionic radii, similar electronegativity, and similar charge density and polarizing power. Lanthanide contraction, the steady decrease in the size of the atoms and ions of elements with increasing atomic number from lanthanum to lutetium. Modern periodic table also known as the long form periodic table, which is based on the modern periodic law, that is atomic number. The periodic table in its current form is known as modern periodic table, which is made 18 vertical groups and 7 periods horizontal rows. Significance of modern periodic table, the classification of elements based on the atomic number, which is more fundamental property of elements. The position of elements in the periodic table is governed by the electronic configuration and it determines their properties. The systematic grouping of elements into 4 blocks, S, P, D, and F, made the study of the elements is simple. Representative and transition elements are separated in this periodic table. Group member represents the valency electrons of the elements belonging to that group. It has removed the anomalies about the position of the isotopes which existed in the Mendeleev's periodic table. Limitation of modern periodic table, their position of hydrogen is still undecided. Group first and group the third A, the group the third A consists of 3 columns without giving any specific name and the number. Inner transition elements are thrown out of the main body of the periodic table. Helium is a place in the P block. However, it is the S block elements. The designation of subgroup A and B is not justified. IPC classification of periodic table, according to IPC system, S block include group first and second, P block include group 13 to 18, D block group 3rd to 12. The earlier notation of designing subgroup, group first and group B of the long form of periodic table is dropped. Difference between the IPC system of periodic table and long form of the periodic table. IPC in long form elements are classified into group first and group 18. Elements are classified into first A to be third A, second B to be third B, and zero group. Subgroups not involved. It is classified into group first A and the subgroups in the long form, but IPC the subgroup are not involved. In this system, in the IPC system, the third is specified 18, 8, 9, and 10. It is divided into 3 groups, but not given the third in the long form table. Noble gases are designated as the group 18, and noble gas is designated the 0 group in the long form. Periodicity of elements. When the increasing atomic numbers, the properties of elements are also repeated after certain intervals due to similar electronic configuration. Cause of periodicity due to similar outer electronic configuration after certain intervals. Atomic size, covalent radii, the atomic size generally decreases from left to right and the increases from top to bottom. Variation of covalent radii in the period, increase in the atomic number, the magnitude of nuclear charge increases while the corresponding addition of electrons takes place in the same principal quantum cell, so that higher nuclear charge pulls the electron more strongly toward the nucleus. As a result, decrease in the size, variation of the covalent radii in the period. For example, atomic size decreases lithium to fluorine. The highest size is the lithium, but least size is the fluorine. That is the cause of the atomic number of lithium is the 3, but fluorine have the 9. So number of protons increases, but size is similar. That's why the atomic size decreases lithium to the fluorine in the period. Variation of covalent radii in the group, the size of atom increases from the top to bottom and descending the group. In the moving down, the atomic number increases as well. The number of cell also added, so that the size of atoms increases in moving from top to bottom in a group. See, in the alkali metals, lithium, sodium, potassium, rubidium, cesium, atomic size increases. So least lowest least size is the lithium, that is atomic number is also least, but highest largest size is the cesium due to atomic number, and also increases number of cells. That's why the size is the increases. Ionic radii increase in moving from top to bottom in the group, decreases from the left to right. Variation in group, the ionic radius increases with increase in atomic number with the group. Since atomic size increases, the ionic radius also increases. Variation in period, size of element decreases along the period, so that ionic radii also decreases along the period from left to right. Ionizing energy and ionizing potential, it is defined as the amount of energy required to remove electron from the isolated gaseous atom. For example, sodium have 11 electrons. If we use the energy to eject one electron, the energy required to eject the electron from the sodium and atom is called the ionizing energy. That is the first ionizing energy, second ionizing energy, and third ionizing energy, and so on. This is the first ionizing energy, IE1. These successive electrons can be removed by the supplying the energy. This type of energy is called successive ionizing energy. In removing electrons, the nuclear charge is same, but number of electron decreases, so that successive ionizing energy following the order. The highest energy is the ionizing energy third, and second, and first, in this, so on. Factors that affect ionizing energy: atomic size. Larger size, the electron is far from the nucleus and easier to remove the electron. Nuclear charge, higher the nuclear charge, difficult to remove the electron from the isolated gaseous atom. Number of electrons is in inner cells. The larger the number of electrons in the inner cells, the smaller is the ionizing energy. Penetration effect, or the effect of SPDF electrons from the same energy cell. Yes, electrons around the nucleus have the greater probability of the combining closer to that nucleus than the PDF electrons, and so on. So closer to the nucleus. Electronic configuration. Certain electron configurations are more stable than the others. If half-filled and full-filled orbitals, the ionizing energy higher than expected. Also, the octet configuration is higher than expected. Variation of the ionizing energy. Variation in the group, ionizing energy decreases in going from top to bottom in a group. The nuclear charge increases, gradual increase in atomic size, increase in inner number of the electrons. Variation along the period. In general, the ionizing energy increases as we move along the period from left to right due to atomic size decreases and nuclear charge increases. Ionizing potential and between aluminum gallium not observed as usual develop contraction. The substantial decrease in the first ionizing potential between the aluminum and gallium not observed is the sodium and potassium and magnesium, calcium. Gallium, argon 3d10 and 4s2 4s2 4f1. It has the 10 d electrons in the penultimate cell, which are the less effective in the shielding the nuclear charge. The poor shielding of the nuclear charge and the electrons cause the stronger attraction between the nucleus and outer electrons, causing the contraction in size in the gallium. This gallium is the smaller due to the d block contraction. The ionizing energy of the gallium is almost equal to aluminum. Ionization of transition element is reasonably constant. The increased nuclear charge would attract the outer electrons clouds with greater force, and hence ionized energy expected to increase from one element to the next transition series. However, as the electrons is added to n minus 1 to this subshell at its next element, the outer electrons are shielded more and more. The effect of increasing nuclear charge is opposed by the additional shielding effect of nucleus provided by the extra d electrons. Consequently, the ionization energy are nearly same. Hence, the first ionization energy of transit element is okay. Transit element is the constant. Electron affinity, the release of electrons by adding electron is called electron affinity. For example, chlorine added one electron, that is the electron is Cl minus. The chlorine atomic number is 17 and added one electron and becomes 18 electrons, that is Cl minus, and releases the energy. This energy is called electron affinity. Factors affecting the electron affinity, nuclear charge, increase in nuclear charge also increase the electron affinity. Atomic size, smaller size of the atom, higher the electron affinity. Electronic configuration, atoms having the stable electronic configuration do not show much tendency to add extra electrons and have either zero or very low electron affinity. Variation of electron affinity decreases in the going from top to bottom in a group and increase in the going from left to right across a period. Electronegativity, the property of atom to attract electron itself is called electronegativity. Pauling after scale of electronegativity, it is on the basis of the Bohr energy of the molecule. For example, A and B, it becomes the AB molecules. For example, hydrogen molecule and chlorine molecules, and becomes the hydrochloric acid. For example, AB, if its Bohr energy is equal to the geometric mean of the Bohr energy AA and BB molecule. So EAB equal to half EAA into EBB. EAA Bohr energy of AB bonds and EA Bohr energy of A bond, EBB the Bohr energy of BB bonds. Difference in Bohr energy, resonance energy, delta equal to EAB experiments minus EAA EBB half. Resonance energy delta of the molecule depends on the polarity of the bond, which depends on the electronegativity difference between the two atoms A and B. Let alpha A and alpha B denotes the electronegativity of A and B. So alpha A minus alpha B 0.12 0182 root under delta. Mulliken's approach of obtained electronegativity, Mulliken suggested that electronegativity could be regarded as the authentic mean of the ionized energy electron affinity. Electronegativity is the half of the sum of the ionized energy and electron affinity unit electron volt. Already in Roko's approach of electronegativity, according to him, the electronegativity depends on the nuclear charge. He defined that electronegativity as the attractive force between the nucleus and the electron. C F equal to Z effective E square over R. ZEF is the effective nuclear charge, is the charge on electron, R is the covalent radius, electronegativity equal to 0.744 plus 0.395 Z over R square. Factors influence the electronegativity charge on atom. Higher the positive oxidation state of atom in the series, the greater would be its electronegativity power, and hence greater would be its electronegativity. Types of hybridization, the percentage of S character increases, the electronegativity of carbon atom also increases. Ionized energy and electron affinity according to Mulliken's electronegativity in arithmetic mean of ionized energy and electron affinity. Hence, higher the ionized energy and electron affinity, higher is the electron negativity. Effective nuclear charge, higher the effective nuclear charge, higher is the attractive powers of the electron. Hence, higher the value of the electronegativity. Variation of electronegativity. Variation in the group, as we move down the group, atomic size increases, effective nuclear charge decreases, so that electronegativity also decreases. Variation in a period, electronegativity of element increases as we move from left to right along the period, increases in effective nuclear charge and decrease in the atomic size, which result in greater nuclear attraction. Effective nuclear charge, the magnitude of nuclear charge which is felt by the valency electrons is called effective nuclear charge and denoted by ZeF. ZeF equal to Z minus sigma. Z is the number of the charge, that is atomic number. Sigma shielding constant, which is the measure of the shielding effect caused by the intervening electrons. Slater rules for the calculation of sigma and Z effective. The value of sigma for an electron residing in an ns or np orbitals of the n shell of an atom or an ion is the sum of the flank contributions each of the remaining electrons in the n shell make a contribution of 0.35 to the values of the sigma. Each of the electrons in the n minus 1 shell makes the contribution of 0.85. Each of the electrons in the next inner cells makes the contribution 1. Remember that each of the remaining electrons in the n cell makes the contribution 0.5. Each of the electrons n minus 1 cell 0.85. Each of the electrons next inner cell makes contribution 1. 0.85, 0.85, 1. Zero value for sigma for one electron present in the n-s orbital of the valence shell. Sigma for 1s orbital, 1 is contributed 0.30. Thus, sigma for electron residing in n-s or np equal to 0.35. Number of remaining electrons in the n shell except one valence shell plus 0.85. Number of electrons in n minus shell plus 1. Number of electrons in inner cells. The value of sigma for electron residing in n-1 d orbitals, n-1 shell of an atom or ion is the sum of the Planck contribution. There will be the no contribution to the values of the sigma for electrons residing in the n-s orbital. Each of the electrons present in n-1 d orbitals makes the contribution 0.35. Each of the electrons present in n-1, ns-p orbitals and inner cells for second, third, and n-2 series makes the contribution 1. Sigma value for n-d electron 0.35. Number of electrons n-d plus 1. Number of electrons 1 minus n-1s, 1-1p orbitals and inner cells 0.35. 0.35 n-d plus 1. Calculate effective nuclear charge at the periphery of the carbon atom Z equal to 6 and sigma equal to 0.35 to 3 plus 0.85 into 2 equal to 3.1. Z effective Z minus sigma Z 6, 3 minus 1, 2.9. Okay, it's all about Unit 4, periodic classification of elements and physical properties under V.C. Foster, Trivandrum University, Institute of Science and Technology, Chemistry, CSEM 101. It's all about Unit 4. And thanks for watching. And request you all like, comment, share, and subscribe. And best of luck. The exam is going to held under 1 month. So I again tell you best of luck. Thanks for watching. See you.